Alright, hey guys, it's Steven Song, and my presentation for my PCB2 final project is on how and why we are able to run. The Homo erectus, or the upright man, is our ancestor 1.6 million years ago. They used fire to cook, they also used stone tools, they had long legs, they ran on two legs, and they used persistence hunting to kill their meals. So, when we went from four legs to two legs, we lost our speed but gained our stamina, and we evolved to persistence hunt. This happens during the hottest time of the day, and the tactics are that the humans would scare, track the animal, and then repeat the process. Eventually, the humans would do this so much that the animal would actually overheat and die of exhaustion. This is all made possible because humans can cool down by sweating while being mobile, while most other animals can't. They actually have to stop and rest. Some adaptations in our muscles is that we have a big gluteus maximus. In fact, it is the biggest muscle in our body. And what this does is it contracts when we run, so we don't fall forward and we don't collapse when we run. It keeps us upright. The arch of our foot, it actually expands and contracts, and what this does is it actually relieves the pressure and acts as a shock absorber from the forces and the pressure of our body weight and gravity. And the main tendon that makes up our arch is the plantar fascia. We also have spongy bone. Our bones aren't completely solid all the way through. And what this feature does is it acts also as a shock absorber, and it bends to the pressure. It's not necessarily completely rigid. And this also makes it lighter for our arms and legs, so it's easier to run. And we have a ball and socket hip, and basically what that does is it makes us more mobile because of all the directions our hip can bend. And what this does is it helps immensely with running around turns and running around corners. It would be very hard to run sideways or run to the side without this feature. We also have a larger valgus angle. We have a larger valgus angle than gorillas do. And what this valgus angle is the angle that our femur creates with our knee. And this helps keep our center of gravity directly over our feet, so we don't have to shift our weight when we walk. If you ever went to the zoo and you saw a gorilla walking on its two legs, you would be able to see it waddle, and this is because they don't have this feature that we do. And our femur is also increased in size opposed to a chimpanzee. It's an increase in size in the caput femoris, which is basically the ball to the socket in the hip. And we evolved to have this because it needed to support more weight as we went from four legs to two legs. Now in the chemistry unit, I'll be talking about cellular respiration and the fuel we need to run, which is glucose. Glucose is created in the small intestine, and it is created through the foods we eat, especially carbohydrates. And glucose is used in the mitochondria of our cell, which then goes through cellular respiration to make ATP. And for marathoners, they tend to carb load, which is when they will eat a lot of carbohydrates in preparation before the marathon. And this is so the marathoner can top off on glucose levels before the marathon. The glucose in our body, it flows through our bloodstream and is necessary to make ATP. However, this glucose in our body can't just get to cells on its own. It has to use insulin, which is a hormone, which allows glucose to get into the cell. So this white thing here is the glucose molecule, and this is the insulin hormone. And what that will do is that the insulin hormone will send a signal to the cell, which will open up the protein transport chains or transport pathways, which then allow glucose to flow into the cell due to facilitated diffusion. Now that the glucose is inside the cell, the glucose goes through glycolysis, the first stage of cellular respiration, to create pyruvate. Then the pyruvate goes through the citric acid cycle, which turns into citric acid, and then the NAD plus turns to NADH, and those electrons carry over to the electron transport chain, which then drop down the electron transport chain and then release energy to create ATP. But the driving factor that allows the electron to be forced to drop down the steps is actually oxygen. Oxygen is kind of like a magnet that pulls the electrons down. And so this is why oxygen is so essential to the human body. It is to create the bulk of our ATP. And now that we've created this ATP, we can use it in our muscles. And the myosin head binds or gains this energy from the ATP, then binds with the actin. And so what that does is the myosin head will attach to the actin, and then it'll contract. And this is how our muscles are able to move and how we're able to run. So most marathoners know the term hitting the wall. And the wall is basically when a marathon collapses around mile 20. And this is due to a lack of glucose because the glucose levels run out in the body, and therefore ATP can't be produced. So the myosin head can't pull the actin, and the muscles are basically stuck in one position. I also wanted to talk about the difference between anaerobic and aerobic exercise. When doing cross country and doing moderate runs, our body works aerobically, which means we use oxygen. However, when we work anaerobically is when we spend more ATP than the bloodstream can supply oxygen to our cells. And this is really ineffective because without oxygen, our bodies can only do the glycolysis cycle, which means for every glucose we only create two ATP. So this is the reason why humans can't sprint for 3 miles, but we can for 100 meters. Now to the physics, Newton's third law, equal and opposite reaction. So basically here we can see the force of friction is equal to the force applied, and so the force the runner puts into the ground is actually also opposite. It goes in the opposite direction. That's how we're able to move forward. We also have levers in our body, and levers are important because it makes work easier and it can use some challenges to our advantage. For example, the weight of our body and gravity, the force of gravity can be redirected into our next stride due to a fulcrum. And because of this fulcrum and because it's a type 2 lever, like a wheelbarrow, the effort goes up and it rotates around the fulcrum. Therefore, the energy can be put into the next stride. So apparently 35% of this energy is used into the next stride, which is very effective and how we are able to save a lot of energy. We also create momentum when we swing our arms, and this allows us to keep us moving. It's easier to keep us going forward without using as much energy. Our arms also help us counterbalance our opposite legs, like a cheetah uses their tails. So arms help us create momentum if momentum equals mass times velocity. So let's say our arm is 3.63 kilograms and the velocity of the arm swing is 2.23. So you multiply those together and you get 8.1 kilograms per meter per second of momentum, and that is actually very effective. Our arms aren't just dead weight, and a study shows that we actually emit more CO2 when we don't use arms than when we do. And this is due to the momentum that it creates. So like I talked about in the bio section, how our feet expands and contracts, and this is due to pressure, and it is necessary for a foot to expand to create more area, therefore decreasing the pressure. So if we have 667 newtons of force into a step, and a foot is 15 square inches, you divide that, it's 55.47 pounds per square inch. However, if the foot expanded 1.25 inches, or square inches, it would equal 41.04 pounds per square inch. And so it is much decreased force due to a larger area, and this is the same science behind why our caput femoris increased in size, is so that it could distribute more weight over a bigger area, therefore decreasing the pressure. And that is all. Thank you for watching.